All right, good morning, everybody. It's 8 a.m. Welcome to VSPG. We have, we have a presentation today by Dr. Kristin Bergmann from MIT, titled Exploring Controls on the Carbon and Oxygen Isotopic Compositions of Neoproterozoic Marine Carbonates. Next week, we're going to hear from Axel Hoffman from the University of Johannesburg, talk titled The Archaean Geological Evolution of the Sigmund Craton, India. So today we have just a short announcement. We've made an interesting mile marker here where we're actually more popular on YouTube than we are via subscription to our emails. So we have maybe 750 people subscribed to our YouTube channel, but I think a little under 700 people getting our emails. So if you know people who are interested in this but not signed up, maybe you can help direct them to the website. We're going to also add links on our YouTube channel for that as well. But with that, we're could go ahead and get started with our speaker's presentation today. Andre, please introduce Kristin for us.
Yeah, it's a pleasure to introduce Kristin Bergmann. She's originally from Michigan and I guess part-time spent in UK. She did her undergraduate degree in Carleton in Minnesota, staying in Midwest with a focus on environmental studies. And when she took a few years sort of to work in real world as a middle school teacher and as well as working for Potomac River doing some studies. And when she went to Caltech for master and PhD, she had 3 advisors, John Gratzinger, Woody Fisher, and John Eiler, which to some degree impacted on her focus or interest. And so she focused on evolution of carbon oxygen cycle as well as clumped isotope record for Neoproterozoic and for Phanerozoic. And she also interested in evolution of carbonate factory and how changes in lithophase affected on climate and affected on precipitation of carbonates through time. And she, after PhD at Caltech in 2013, she went to Harvard University to be a junior fellow in Society of Fellows in Harvard University, worked with Andy Knoll, and started her position in MIT as assistant professor in 2015. So with this, it's a pleasure to pass to Kristin.
Thank you so much for the invitation to come talk, and thank you everyone who is here to listen today. I promise I will say some controversial things during my talk today. So I'm just going to go ahead and share my screen and dive right in. Let me just hide.
We can see your screen.
Okay, great. Okay, so in terms of thinking about the Neoproterozoic carbon and oxygen isotope records, I'm going to begin by just acknowledging the amazing group of junior scientists that I've been able to work with at MIT, shown in blue, and many of them have moved on to other places, which is really exciting. And then also Tamara Pico and Ali Laub have also contributed to what you'll see today, and also the resources from these various institutions. So when I was a first-year graduate student, I fell in love with this pink and purple rock from outside of Death Valley in California. And this rock has these beautiful, delicate seafloor precipitates of calcium carbonate that nucleated on a sediment water interface and grew up into the water column. Associated with these amazing crystal fans within the same unit are these radial with crystals growing outwards, ooids that are composed of dolomite today, as well as an abundance of heavy minerals like iron oxides, titanium oxides, zircons that are in and amongst the crystal fans. And also in and amongst the crystal fans are radial ooids with crystals growing outwards that are composed of calcite today. And I was even more excited as a graduate student when I found really similar things in Oman. So similar radial ooids composed of dolomite today, abundance of heavy minerals, and radial ooids composed of calcite that looked a lot like these poorly abraded ooids from California, but also sometimes they grew bigger and more beautiful, like you can see here. And so these unusual carbonate fabrics that you see in California and Oman are associated with the Shurm excursion, which is the most negative carbon isotope excursion in Earth history, and it's coupled to this excursion in Delta O18. And I'm showing the Shurm excursion here in red, so you can see this big drop in Delta C13. And if you look forward in time, it really has no comparison over the last 500 million years. I'm also showing a mineral Delta O18 record that I'm going to come back and talk about creating later. But I do want to point out that I've weighted quartiles within the data showing what's likely the best preservation with the darkest color. So in Delta C13, we tend to think of that as the 50th percentile, the median, but in Delta O18, that tends to be the heavier Delta O18 values because multiple alteration processes drive Delta O18 light. And so that brings us to the first controversy that we'll touch on today, and that's this controversy over what the carbon isotopic record of the Neoproterozoic means and what was driving these really big swings and variability in these shallow carbonates. And so in the Phanerozoic, we normally think about Delta C13 as a function of the strength of biological pump, the ratio of inorganic to organic carbon burial, as well as the importance of respiration, even PCO2 and temperature on the biological and inorganic systems. But we also know that Delta C13 can be altered, particularly in situations with high fluid flow. And so because the Shurm excursion is so negative, there have been a host of hypotheses that this excursion has to do with alteration of carbonates. And this includes meteoric alteration, deep burial alteration, post-depositional precipitation of particularly light carbonates from remineralized organic carbon. And finally, that there are differences in the amount of water rock conditions and fluid flushing throughout this stratigraphy. And that's under this assumption that all of these rocks were originally aragonite, and that's based on calcium isotope patterns. And then the second controversy that we'll also spend time thinking about is the oxygen isotope controversy. And so when you think about the Delta O18 of various minerals, not just carbonates, but cherts and iron oxides, as we heard from Itai a few weeks ago, and apatite, there's a decline to more negative values as you go further back in time. And the Delta O18 of carbonates and other minerals is a function of temperature, the Delta O18 of the fluid that they precipitate from, as well as alteration and the mineralogy that is forming. And so there have really been three hypotheses for why ancient rocks preserve these more negative Delta O18 values. So one is that the seawater Delta O18 composition has evolved through time and it's become increasingly heavy. The other is that Earth's climate system and temperature has evolved over long geologic timescales, from warmer temperatures to more moderate temperatures today. And finally, there's also a possibility that the older rocks you get, the more altered they are. And so one thing that we'll spend a lot of time thinking about today are oxygen isotope systematics, because I think that they're really worth interrogating over both short and long timescales to explore both of these controversies, because at their heart, some of the hypotheses have to do with alteration, temperature, and different fluid compositions. So the first thing I want to do is compare the Sherm excursion to two recognized climate events from the Phanerozoic: the Permo-Triassic mass extinction, one of the biggest mass extinctions in Earth history, and the PTM, or the Paleocene-Eocene thermal maximum. And if we look at the delta C13 and the delta O18 across each of these excursions, you can see how extreme the Sherm excursion is. The negative excursion in carbon at the Permo-Triassic boundary isn't even really showing up, but you can see a negative excursion in delta O18, but it's not to the same magnitude. And for the PTM, the benthic record is this really thin record with the planktonic overlaid. And again, see how small the signal is in delta O18 space for the PTM. I'm going to have two reference lines on these plots for the talk. So in the water delta O18 plot, you'll see a gray line that's at about minus 1.4 per mil, which is what we think seawater would be today if we had no ice. So it's an ice-free seawater composition. And then the other line is this temperature at 38, 39, 40 degrees, where a lot of macroscopic complex eukaryotes tend to get pretty unhappy. So the first thing that we can do is we can consider what a moderate temperature profile across the entire excursion would look like. So we plug in a constant temperature of 25 degrees C, and we calculate what the water delta O18 change would look like over the excursion. And when we do that, you can see that for the Sherm excursion, compositions range from an expected ice-free composition to very negative, with the median of all of the data sitting at maybe -5, -6 per mil. We can also do the exact opposite and take a delta O18 composition of an ice-free ocean of -1.4 per mil and calculate temperature. When we do that across the Sherm excursion, we see that the delta O18 could also represent higher temperatures in the middle of the excursion, either from primary processes and climate change or burial processes. And we can do the same approach for the Permo-Triassic and the PETM, and you can see that the expectations for either water change or temperature change are smaller for both of these Phanerozoic coupled excursions. We can also go back and compare the Sherm excursion to other Neoproterozoic negative carbon isotope excursions. And the first thing that I would point out is that other Neoproterozoic carbon isotope excursions are similarly filled with beautiful and weird carbonates, including in the Bitter Springs excursion from Svalbard, these molar tooth calcite cements filled with talc, and seafloor precipitated crystal fans like we had from California. And then, for example, from the post-Marinoan cap carbonates, you see stromatolites with a lot of vertical inheritance and suggestions of rapid precipitation. And so if we do the same approach for these other excursions, you can see similarly that we're either looking at a big change in fluid composition across this excursion or temperature. And so this is worth understanding. So if we think about Earth's habitability through time, it's really important how we got from here to the modern system. And in particular, Earth's temperature profile through time is a critical state variable. We already have evidence that some aspects of the climate system have changed, because the Neoproterozoic is characterized by these low latitude equatorial ice sheets, and the Phanerozoic is characterized by high latitude glaciations. And modeling efforts have predicted a wide range of temperatures for both the glacial low latitude conditions, but also the post-glacial conditions, even up to temperatures as high as 50 degrees C. And so to think about whether it's even possible for the Earth system to have entertained both very cold and very hot climates in the Neoproterozoic, we need to think about the carbon cycle. And in particular, I'm going to talk about the carbonate component of the carbon cycle because it is a significant sink for CO2 over geologic time. And so this carbonate reservoir and carbonate fluxes are large. So today we have a carbonate flux in open ocean environments from planktonic calcifying organisms, and they create this large deep sea carbonate reservoir. We also have shallow water carbonate flux going into coral reefs, and they create this shallow carbonate reservoir on continental crust. And so if we look at a map of the distribution of these two across the seafloor in dark blue and across the continents in light blue, we can see that they have very different systematics over geologic timescales. So the deep sea carbonate reservoir is responsive. The planktonic calcifying organisms overproduce in the shallow oceans, and CO2 then is efficiently reintroduced into the mantle at subduction zones. The continental carbonate rock reservoir, on the other hand, is stable over long geologic timescales and doesn't have an efficient way to return to the mantle in the same way that deep sea carbonates do. And so this question of when and where was the continental rock reservoir built is critical. So when we want to understand the nature of the continental rock reservoir through time, it's important both for thinking about it as a CO2 sink, but also for some of the questions we were thinking about with these excursions and whether they are driven by alteration or primary processes. And I would argue that the rock record has relevant information about this question at all scales. So the petrographic scale is important, the facies scale is important, the stratigraphic scale is important, and then the global rock record is also important. So today I'm going to spend time thinking about this global carbonate rock record. And so what I'll present is a data set that I created by combining a publicly available global lithologic map and continent scale geologic maps that have age information, and put that all into G-plates to get paleogeographic information for all of these carbonate polygons through time. And so I'm going to start by showing a movie of the distribution of carbonate rocks, mixed carbonate siliciclastic rocks, and siliciclastic rocks through time, with the caveat that over the course of the Neoproterozoic, the age resolution within a lot of these geologic maps is poor. So that's an area that could be improved. So we're approaching the Neoproterozoic to Phanerozoic boundary. We hit it. This is the Carboniferous. The Cretaceous. And the Cenozoic. Okay, so if we take all of those polygons of siliciclastic rock area and we look at the component of the whole record that's represented within any time interval, we see that 7% of the siliciclastic rock record is represented from the entire Proterozoic, so from 2.5 billion years ago to the Precambrian Cambrian boundary. And the whole profile represents one that we might predict from erosion dominating the siliciclastic rock record. But that's different than what we see in the carbonate rock record. So across the Neoproterozoic to Phanerozoic transition, with this approach, we see an increase from 5% of the carbonate rock reservoir from Proterozoic rocks to 30% of the carbonate rock reservoir represented in early Paleozoic rocks. And this is a 172% increase. And this increase coincides with the termination of the Great Unconformity, which is the flooding of a lot of old igneous, metamorphic, and sedimentary rocks after a big gap in time. So here now I'm showing the range of transgression that you see associated with the termination of the Great Unconformity. And if we look at each individual paleocontinent, you can see, or modern continent, you can see that the increase across the Neoproterozoic to Phanerozoic is concentrated on a few continents, in particular Russia, North America, and the Arctic, as well as to some extent China. And if you look at the same thing, just the area in Salicylastics, so we're comparing apples to apples, not accounting for the time difference in these bins, but you see that the Salicylastic area is decreasing on almost all continents and doesn't show a big change across the flooding associated with the end of the Great Unconformity. And so we can ask what the paleogeographic distribution of North America, Siberia, and North and South China was. If we bin all of the polygons, we can see that this increase in carbonates was equatorial, which is great. We know carbonates tend to be happy at the equator. And we can also see other big increases in the carbonate rock reservoir, like in the Cretaceous. We have zoom in back to the paleogeographic maps. We can see that North America, Siberia, South China, and North China were equatorial before the transition into the Phanerozoic, and they were not accumulating significant carbonate. But then after, by the early Ordovician and Silurian, you see carbonate rocks in this database. And I would argue that this approach that I've done probably underestimates the amount of carbonate that even exists today, despite erosive processes on North America, Siberia, and North and South China. So this is a different global geologic map from Macrostrat. And you can see the Cambrian and Ordovician deposits in green and the Ediacaran deposits in pink. So now we're going to explore whether this carbonate increase could have been a consequence of life getting big and complex. So also associated with this transition, of course, is the advent of biomineralization across a range of taxa. And you can see that the planktonic calcifying organisms didn't evolve till much later in the Mesozoic. So if we think about carbonate platforms grade to sea level, and they prograde away from shorelines. But if biomineralization drove efficient carbonate precipitation, you could still aggrade a Phanerozoic, early Phanerozoic carbonate platform to sea level, but you would overproduce carbonate sediment and prograde much further from shore. So there's this potential process that Precambrian carbonate platforms were smaller because they were kinetically inhibited, and Phanerozoic carbonate platforms could grow much bigger in the early Paleozoic because biologically mediated carbonate precipitation took off. I think there are two things in particular that I would think about as really big levers on the Precambrian carbonate platform system. So the first is the role of magnesium in these platform environments. Magnesium is much more strongly bound with water. And when you have a lot of magnesium in solution, you can see effects on calcite precipitation rate and calcite morphology, and even get to the point where you're precipitating protodolomite or dolomite on the right conditions. I think the other one is Salicylastics. So a lot of Precambrian carbonates are closely associated with Salicylastics. And so if these platforms could not prograde as far from shore, then they would always be associated with Salicylastics, which can easily drown the carbonate factory. But biomineralization could have overcome the first inhibitor by evolving calcium proton coupled pumps, which saturates calcium in the space where carbonate precipitation occurs, plus all these other components like carbonic anhydrase. And if these carbonate platforms were able to prograde further away from shore, then they would be further from salicylastic inputs. So if we're growing larger early Paleozoic carbonate platforms, this could have a positive feedback with subsidence. So a large carbonate platform will load the crust and create more space for precipitating carbonate out of seawater. So in effect, you're able to enhance CO2 sequestration by sediment loading. And so we can look at this possible effect with a data set from North America for macrostrat. So what we're going to look at is a cross section through the uppermost continental crust, and we'll look at different sedimentary lithologies and plutonic and metamorphic rocks, as well as their thicknesses through time. And I'll just show one here from 40 degrees north now, from A to A prime. And if you look at the data in this space, some of you might be familiar, it looks a little like a Wheeler diagram. And you can see this plutonic and metamorphic succession, a big gap in sedimentary rocks. So this would represent the great unconformity. And then flooding of North America, a lot of blue, and then less blue above that. If we zoom in on this interval where we see significant carbonate, we can see this flooding of North America and precipitation of carbonate. And what we see with the carbonates are they tend to be thicker on the margins of the continent, thinner in the interior, but the interior is still carbonate dominated over this interval. So then we can plug those thicknesses and time intervals into a model coupled to the North American crust, where we can predict the sea level increase associated with the sediment load. This is work that I've been doing with Tamara Pico at UC Santa Cruz. So what you see if you look at the salicylastic load is that it's concentrated in both the Ediacaran and the early Paleozoic in tectonically active basins, like that associated with eastern margin today, that was a tectonic orogeny in the early Paleozoic. And if we do the same thing over these two time intervals for carbonates, we see an increase in the carbonate load as you move into the early Paleozoic, and that sediment loading is broad. It's across the entire continent, which could have this effect of amplifying sea level rise and increasing accommodation. So I would argue that maybe we're seeing the great unconformity as a big signal because of equatorial carbonate forced flooding, and it's the termination of it that's as important as anything, given that gaps in the rock record are a dime a dozen. So if we think about this potential model from the late Neoproterozoic to today, we have continents with small continental carbonate rock reservoir on the margins in the late Neoproterozoic, composed predominantly of microbial carbonates and abiogenic carbonates. In the early Paleozoic, we flood these equatorial continents, load the crust, precipitate out a lot of carbonate, draw down PCO2 and DIC. And we do that through organisms like rugose corals, trilobites, brachiopods, calcifying algae. And then today, obviously, we've also now evolved planktonic calcifying organisms, which increases that deep sea carbonate reservoir. We also have a much more exposed rock reservoir on continents that will increase weathering from carbonates. Okay, so this model makes a very specific prediction for the time scale of PCO2 and temperature change. And so now we can go back to these isotopic records and explore that further. So if you were to go to the literature, the current high resolution delta O18 record is fossil based. So in the Cenozoic to Mesozoic, we have benthic foramens, planktonic foramens, and then we have tropical, subtropical fossils like brachiopods and belemnites that were coastal. And considerations of carbonate rock delta O18 are usually avoided at all costs. So they're shoved into the supplemental materials if we're lucky, and maybe plotted in a cross plot to think about carbonate alteration and diagenesis. But I was able to convince others to take a risk and put some time into thinking about delta O18. And I'll particularly highlight Julia Clark's efforts in this. And some of these folks also contributed to the clumped isotope data that I'll show at the very end. And I just wanted to recognize all of the publications that have gone into this effort to build a high resolution carbonate rock delta O18 record across the last billion years. So these authors have done an amazing amount of work, and we just went in and found this dark data. And so now what you can see is that we actually have a lot more data. You can see the counts in 5 million year time bins for limestone as well as dolomite. And this is what the data looks like in its raw form with benthic and planktonic records. Again here, where you see the benthic deep sea is heavier because it's colder in the deep ocean. And then we have a lot of overlap between these coastal fossil materials and coastal carbonates in the Paleozoic. And in the Precambrian, we see this duality between dolomite and limestone. So the first thing that we can do to better understand what carbonate bulk rocks are telling us are we can compare it to this tropical fossil record where they're likely preserving the very similar ancient environments. So the Phanerozoic fossil delta O18 record is usually treated largely as a temperature record of these coastal environments. And so what I've done is I've, again, used a constant seawater of -1.4 per mil through time and translated that into a temperature for the calcite rock record that you can see here. And then I've subtracted the Phanerozoic fossil record from that so you can see the offset or the residual. So for a lot of the early Paleozoic, we actually see really good agreement between the median in the limestone data and the median of the fossil data, the 25th percentile and the 75th percentile in both data sets. And then there are other time periods that also agree well, although I will highlight that we have less data in both of these records over the Cenozoic. And a lot of times this record, these records are in agreement within 5 degrees C, which are these two lines here for reference. And I would like to highlight that this one interval of time when we see significant disagreement between these two records is an ice house, the late Paleozoic Ice Age. And we see both evidence in the rocks and have an expectation for extensive meteoric alteration of platform carbonates that were exposed and then submerged and exposed and then submerged. And it's really similar to what our modern carbonates in platform environments have undergone over the recent glacial and interglacial cycles. So modern carbonates are not the best carbonate to look towards as a reference of how reliable the long-term delta O18 record of carbonates is, I would say. Okay, we can also compare the dolomite record and the calcite record, again, translating them both into temperature using a constant seawater through time. So again, here's the calcite temperature record with that approach and the residual in dolomite space. And you see a really cool thing where almost, across the whole Paleozoic, dolomites are hotter than calcites in this approach. But in the Precambrian, we have really good agreement in the Ediacaran and the Tonian between these two records. And I think that actually works really well with what we see in the dolomite rock record across this transition. So a lot of dolomites in the Neoproterozoic are beautiful and likely had this dynamic of magnesium sitting on these crystal surfaces and helping to drive dolomite precipitation. So we have ooids, fenestral mudstones of really tiny dolomite crystals, dolomite spherulites. And that's very different than what we see in dolomites in the Phanerozoic, where they're composed of the classic rhombohedral textures and are visibly replacing other rocks. Okay, so then the last test of the delta O18 record that we can do is use carbonate clumped isotope thermometry, which is a function of just temperature and not seawater or fluid delta O18, but it is also a function, just like some of these other proxies, of alteration and solid state reordering. And I think it's helpful to think about clumped isotope measurements as even more sensitive than delta O18 measurements in carbonates to alteration and resetting. And so if we take the long-term record from carbonates, here we have the delta C13 record up top, and we've done the same thing that we were doing for the early exploration of specific excursions. And we've translated the mineral delta O18 record either into an expectation for seawater delta O18 through time with a constant 25 degrees C for an equatorial temperature, or we've translated that record into temperature using a modern ice-free seawater composition of -1.4 per mil. And if we overlay temperature measurements from a whole range of carbonates from fossil materials, as well as dolomites and limestones, you can see that there is a really big range in clumped isotope temperatures for a lot of different time intervals. And so that large range is this function of alteration and solid state reordering in these different systems and environments. But we can also see that even back in the Neoproterozoic, we're preserving cool clumped isotope temperatures in some sections, and those tend to be sections that are more shallowly buried and well preserved, like Oman or Australia. And so if we take those clumped isotope temperatures and we look towards the minimum of that distribution and take the 10th percentile of each of these records, you can see that that 10th percentile of the clumped isotope data is approximating the median of a delta O18 extrapolated to temperature record. So next, we can take those lower bounds on temperature from clumped isotopes and plug them back into the mineral delta O18 composition and gain another approach to considering seawater delta O18 composition through time. And when we do that, we see that the best preserved materials with clumped isotope compositions that are 30 to 40 degrees in the Neoproterozoic are giving seawater delta O18 compositions of -1.4 per mil, or even heavier, as you might expect during a glaciation like the Sturtian. We can zoom in just to see this record a little bit more at a little bit more high resolution. And you could imagine what it would look like to continue to populate the clumped isotope record in the same way that we've populated the delta O18 record. But critically, over this interval when seawater has been predicted to drop dramatically to -6 per mil in the early Phanerozoic and then continue to drop over the Precambrian, we do not see evidence for that in the clumped isotope data. And instead, we see evidence that the temperature system has changed. And I'll also just suggest that you keep your eyes out for a record that I'm not showing here, but that one of my graduate students, Julia Wilcox, has been doing a great job with building clumped isotope data out across the Tonian from Australia, and the temperatures that she's getting fall right in line again with a median or lower bounds of the delta O18 predicted temperatures. And so if we return to the rock that started it all from outside of California and these crystal fans, and go back to the Shurm excursion, we can look at this large drop in delta C13 space and I think feel much more confident that we have a mechanism to have the delta O18 record represent temperature, so that this excursion is recording a climatic event where the peak of the negative carbon isotope excursion is associated with the warmest temperatures, and then there's a cooling following the carbon isotope recovery, much like we see in the Phanerozoic across the Permo-Triassic or the PETM, but the magnitude in both of these systems is bigger. And I think that's because, like I suggested earlier, we did not have this very large continental carbonate rock reservoir. And importantly, we see the first really beautiful macroscopic fossils on a mistaken point that are much more detailed than things that came before them right in here during this cooling associated with the end of the Shurm excursion. And so if we think about the evolution of our planet from where it started to where we are today, I would argue that the advent of carbonate biomineralization was critical for stabilizing the isotopic records we see in delta C13 and delta O18, and also the carbon cycle and climate system. And it did this by sequestering carbonate and CO2 on continental crust, and that is relatively resistant to erosion. Okay, and so at this point, I've touched on a range of controversies. The Neoproterozoic delta C13 record, is it primary or diagenetic? The mineral delta O18 record, is it seawater or temperature changing? Snowball Earth glaciations and the temperature associated with them, the great nonconformity, and the evolution of complex life. So I'm happy to take questions.
Thank you very much, Kristin. It was really interesting. Well, we can give people some time to come up with their questions. You can either type it into the chat and I can ask it for you. You can raise your hand. I want to go over how to raise your hand again. If you go to the reactions at the bottom of the screen, there's a box that pops up. Along the top, of that box, there are emojis. At the bottom, it says raise your hand. You have to click that button. So that is the way to raise your hand if you'd like to ask your question yourself.
No questions.
Maybe
It usually takes people a moment.
I can start with general question. So So it seems like you implying that were factors that inhibited carbonate precipitation. But can you maybe tell more about how you see carbon cycle? Because if you, it sort of would result in building larger dissolved carbonate reservoir, but eventually amount of carbon dioxide that come to atmosphere has to go down. So what would be a process if you have a smaller carbonate factor? Do you imply reverse weathering, or what process as well?
Yeah, a couple of components to this. I would say the first component is that I think we do see evidence in the rock record of these carbonate platforms overcoming some of those kinetic inhibitions and precipitating more carbonate. And we see those in kind of the aftermath recovery intervals of these large negative carbon isotope excursions, suggesting that silicate weathering is picking up when you have CO2 perturbation associated with these excursions. I think the other aspect that I'll just go back to highlight through all of the references. Okay, yeah. So here, another component that I think could be critical for thinking about the dynamics of the carbon cycle and how imbalanced it is CO2 outgassing. And so today's rates are high enough that we tend to think of them as a really important lever that we have to take through time. But actually, I'm wondering if CO2 outgassing rates were smaller after the kind of early initial formation of the ocean atmosphere system, and so that you could balance a smaller carbonate flux with a smaller CO2 influx. And the reason then that we would change to larger rates that we see today is because of this onset of a very large deep sea carbonate reservoir. And so CO2 outgassing rates would increase associated with that and creating more of the deep sea carbonate reservoir.
Thank you. I'll ask a couple more, but I'll let other people go.
Yeah, we have several people have questions in the chat now. So Greg Vitalik, your ocean temperatures are between 40 and 90 C in the Precambrian.
No.
Is this compatible with life in the sea?
No. So yeah, I'm showing the delta O18 as deciles so that you can get a sense for the total range in all of carbonate delta O18 data, but I've done nothing to first screen for locations that have more alteration expected with them because they've gone down to high temperatures and pressures like the Death Valley succession. And so I think what I would appreciate you thinking about this record as the best estimate for temperature is going to be the lower quartiles. So the 25th, the 50th percentile at most. And so for almost all of the Neoproterozoic, the median of all of our delta O18 data is below 40 degrees with all of the data compiled like we've done. And it's only during these carbon isotope excursions when we actually see temperatures that are a little bit hotter. But if you look at the Sherm excursion, for example, you know, it's not everywhere that is hot. It's the coastal environments that we're preserving in these carbonates. And so I definitely think that life can live through these high temperature events. Yeah, I do not want you to take away that I think that the oceans were 80 degrees C. So that is a sign of alteration.
All right, the next one is from Ben Johnson. It says, thank you for the talk. I may have missed it, but does the growth of the continental carbonate record indicate something about the area of emergent crust or passive margin area? Just curious about the mechanism of continental carbonate sequestration.
Yeah, so I guess what I would say that I think that if this mechanism of crustal loading from carbonates to drive more carbonate deposition and crustal loading in the interiors of continents works on these equatorial continents in the early Paleozoic, I think the one thing that it says is that the continental topography was relatively low. So we had large regions of these equatorial continents that were relatively flat. Yeah, that's as far as I'm going to go on emergent continental crust.
Okay, next one is from Human Bao. Kristin, great work. Can you speculate on the cause of warming during the Sherm excursion?
Yes, absolutely. Okay, so we'll go to the end of the extra slides. Okay, so one thing I did to think about the external mechanism that could have helped drive the Sherm excursion is look at the kind of whole range of volcanic activity across the Neoproterozoic. And so in the early Neoproterozoic, we have this abundance of gabbros, mafic dikes, the Franklin-Larginus province, mafic volcanics. But in the Ediacaran, we've switched to volcanism associated with the opening of the Iapetus, as well as the Pan-African orogeny. And so here we actually see a lot of carbonatites in this light yellow color and some other unusual volcanics that I think could actually be telling us that there was a lot of CO2 outgassing associated with this volcanism. And we also would expect that there's an internal mechanism to also amplify temperature increase, where if you have a large DIC reservoir in your ocean and you warm it, then you're going to be able to add CO2 from the ocean to amplify a warming from external perturbation.
Okay, we have one more in the chat from Jenna Johnson. Awesome talk, Kristin. Can you expand on what the carbonate cycle is looking like in the Archaean Proterozoic based on your global compilation? Is there limited shallow carbonate deposition and no deep water carbonates? Could this be driven by carbonate saturation changes because of higher CO2 as well as biomineralization?
Yeah, so certainly, I would say the further back in time we go, the more we have to contend with the importance of erosion. And so I feel very good that we understand what was flooded and what was not flooded since the Sturtian, to know that really in the late Neoproterozoic versus the early Paleozoic, we have a really big difference in that continental carbonate rock reservoir. I think it's much harder to think about for the Archaean and the early Proterozoic. And I guess I would say in terms of, we know we have carbonate platforms, so there's obviously still a sink, but I think it's possible that it's either way, right? So either there was a larger continental carbonate rock reservoir that was eroded, or this kinetic and physical inhibition kept the carbonate component as a smaller flux. I'm only talking relative here. Yeah, and in terms of the deep sea carbonate rock reservoir in the Precambrian, I mean, I think we need to remember, saturation state, that saturation profiles that we're only going to get, it's only going to get harder as you go down in depth. And we don't have a pelagic flux. So yes, there might have been carbonate precipitation associated with hydrothermal alteration, seafloor precipitates in the deep ocean, some carbonate coming off of platforms and depositing offshore. But I think all of that is more minor than what we have once we evolve planktonic calcifying organisms. And I think that fits with the rock record that we do have from deep water environments, particularly in the Precambrian, that tend to be very carbonate lean.
Great. We have another one in there from Brian Pratt. No doubt that biomineralization was important, but most lower Paleozoic carbonate platforms were overwhelmingly composed of lime mud. How does that jive with your evolutionary model?
Yeah, great. agree, right? It's, yeah, so if you look at the volume of an early Paleozoic carbonate that's skeletal today and the volume that's mud, the volume of skeletal material would be small. So I think that there are a few options, right? One is that there are organisms that became carbonate mud and were still a really big component of producing the carbonate platform, carbonate. And another option is that, you know, we have processes to abrade carbonates that's fossils so that we don't see them. And we create that mud by abrasion. So I think probably both are in play. You can also have a situation where the carbonate biomineralizers are important for creating the platform and the geometry and the progradation, but you're still able to fill in the platform with abiotic carbonate precipitation. So it could be a mix. And I would also say after the Great Ordovician biodiversification event, that changes a lot, right? So that early Ordovician, we actually see a big increase again in the carbonate if we zoom in and look either in North America or across higher resolution estimates of carbonate versus siliciclastic rocks through time.
I guess now I'm sort of wondering if there would be a way to test the biomineral sort of influence on lime mud deposits. I mean, I wonder maybe you could do something with organic matter and you could look at biomarkers or something. I don't know. Do you have thoughts?
I guess not specifically to tie it to biomineralization derived mud. But I will say that, you know, I think it's important to think about John Husson and Shannon Peters' effort that suggests that these rocks are associated with more organic material. And so that you're not only burying more carbon during the early Paleozoic, you're also burying more GOC. So who knows where that comes from, but it seems to be preserved in the rock record.
So that's all we have in the chat right now. Andre, you wanted to come back to some things, right?
So Kirsten, I was impressed by this change in carbonate precipitation from Neoproterozoic to Phanerozoic, and I kind of need to think about it more. But did you consider possible bias, like, for example, like Salicylastic sediments would likely to be preserved on the continents, and carbonates would be pushed in areas with limited supply of Salicylastic sediments, so they kind of would be pushed more on continental margin or farther away. In other bias, that carbonates probably more easy to dissolve and remove from the geological record compared to Salicylastic. And other thing like might not be relevant, but we work on Baltica, and so in the current time, Baltica and I think Namibia sort of position more or less at the same latitude, and Namibia the current record is full of carbonates, and in Baltica you cannot find any carbonates across whole Baltica. And what I was thinking potentially could be at least two explanations. One is that it's time of orogenic events in Baltica, but it's the same in Namibia, so that's probably not the main factor. But the second one, that Baltica, exposed area of Baltica at that time was mostly sort of crystalline metamorphic rocks, so you don't recycle much of carbonates, whereas in Namibia was plenty of Tonian carbonate, but you can recycle and keep carbonate precipitation going.
Yeah. Okay, I'll maybe just have one comment on the last thing that you said, and then I'll revisit the earlier questions. So similarly, like, working in Oman, the end ediacaran carbonate platforms of the Bua and early Ara formation are really thick and abundant and large. So I'm not saying that carbonate platforms don't exist, they can't grow big. It's just that the scale, I think, changes significantly. Yeah, and I think especially if there are kinetic and physical controls on Neoproterozoic carbonates, then I think you might expect to see these differences across continents, even though you're in a conducive paleolatitude in a way that maybe you don't see as much in the Phanerozoic. Okay, now I have to remember where you started. Can you remind me?
About preservational bias.
Oh, yeah. Okay, so on one side, I think if you have a stratigraphic unit that is interbedded carbonate and siliciclastics, you're not going to preferentially weather out the carbonates and miss those. So I think that when we can estimate the amount of carbonate from working up sections versus siliciclastics, I think that's a really good metric of how much carbonate to siliciclastic there was in the Precambrian versus the Phanerozoic. I guess I could, so like if you look at the percent carbonate versus total sediments, you also see a jump in all of these different records from the Neoproterozoic to Phanerozoic, and this is macrostrat, which is higher resolution, earth chem, so geochemical data of carbonates, to other sedimentary rocks, Roanoff's original compilation, as well as this global lithologic map effort that I did. Yeah, I don't think we're going to preferentially weather them from the same section, but the other aspect of your questions, is there a bias based on where these rocks are? I guess I would say, if we look at the siliciclastic record over time, it almost suggests the opposite pattern, right? Where siliciclastics are easier to erode and remove because we do see that exponential decay from the recent to the ancient versus carbonates that are preserving this signal. And so, maybe there's no reason to assume that that's any different, that if your siliciclastics are dominantly depositing in tectonically active basins, they tend to be the ones that are getting more recycled. Yeah, so I guess that's where I'm going to leave it, unless you want to have a follow-up.
I think
has a question, so maybe
yeah,
I come back later.
Yeah, go ahead, Paul. And I think we're solidly in the area of open discussion. So let's, if people want to step in and open discussion, but Paul, go ahead.
I just wanted to point out that the Roanoff database was compiled in the 1950s. I know it was published later, but it was compiled in the 50s when there was virtually no radiometric geochronology. And there's no way of updating that data set because the locations are only identified by continent. And the macrostrat database was compiled, at least for the Precambrian, in strictly pre-1970 data. The only reference given in macrostrat for the Precambrian of Canada is Geology and Economic Mineral Deposits of Canada, published in 1972, compiled in the late 1960s. And at that time, there were virtually no radiometric constraints, direct constraints on sedimentary sequences. Basically, the only geochron was potassium argon ages on metamorphic micas. So I have, serious reservations about these data sets.
Yeah, I'm just going to go back to this. So I would love to have a fully updated Precambrian data set. And I don't think that this global approach that I've used is that either. So some of the continent scale geologic maps, like the North American USGS maps, have somewhat better edge constraints, but they're rarely better than the Akron and Tonian. And yet I would say that even without radiometric age constraints, we can recognize Precambrian versus Phanerozoic rocks. And so this component of this record, that 2.5 billion years or 2 billion years of Earth's history, represents 5% of the area today versus 30% for this very short period relative from the early Paleozoic. I don't think that that's going to go away. Even if we have this higher temporal resolution in the Precambrian. You can prove me wrong, but that's my instinct looking across these data sets.
Well, there's no doubt that the Neoproterozoic is poorly represented in Laurentia by area.
Yeah, but this is based on all of these continents geologic maps. And there are plenty of other places that, you know.
Well, as I say, the non-North America data, if it's from Roanoke, I mean, it's strictly a guess as to what the ages are.
It's not from Roanoke. It's from the USGS-based continent scale geologic maps. So, yeah, it's a very different data.
Well, but the maps only give the area that's exposed. So
Yeah,
in Gondwana,
absolutely.
there's a lot of cover.
Yeah. I agree that that is an area that we can continue to improve. I would love to have the full cross-section like we do from macrostrat for other continents. I think that would be amazing.
I mean, I can tell you that for Congo Craton, which is the size of, the USA, the entire craton is covered by Neoproterozoic carbonate, but very little of it is exposed at the surface.
Yeah. Yeah, I certainly think it's an area that we need more work in to continue to improve this style of data, but I do think that we need to be thinking about the global rock record to understand these large-scale trends.
So, Kristin, just following on it, your diagram kind of give impression that it was very sharp change.
Oh yeah, but it's
Cambrian boundary, which so what do you think about it? And if it's indeed sharp change, what assuming that your record is correct, what it would be explanation for it?
Yeah, hold on. Okay. I don't think it was a sharp change. I think that's an artifact of these geologic maps spinning all of the Cambrian rocks into a Cambrian time period. And so the approach that I used where I turned on the polygons that were Cambrian aged all at the same time, because there's no other higher resolution, makes it look sharp. But if you look in North America, you can see that the carbonate deposition is gradual, associated with the transgression to the interior of the continent. And we see variation over this time interval from the Cambrian through the Indo-Ordovician glaciation.
Doesn't carbonate production always have to be in balance with alkalinity input from weathering?
Yeah, so the alkalinity side is something that I would love to think about more with anyone who's excited to think about that with me.
All right, anybody else have some points of discussion or questions? Okay, well, great. Kristin, this was a really good talk, really great record you showed, and we got some good discussion. So thank you so much for presenting for us today.
Yeah, thanks for everyone for listening and asking great questions.
Yeah, so everybody take care until next week when we hear from Axel Hoffman. All right. Bye, everyone.